Alright, moving on, doing more practice of related rates. So nothing else is really changing, it's just more practice. So, number one, a plane is flying away from an airport at an altitude of 5 miles. When the plane is 10 miles away from the airport, the distance from the airport to the plane is changing at a rate of 240 miles per hour. What is the speed of the plane? So I want you to try and solve this, draw a picture, and find the speed of the plane. Alright, so we should end up with the speed of the plane is 32 root 15 miles per hour. We get that. So this is the picture I drew. If this is the airport, the plane is 5 miles altitude, flying away from the airport. So I call this distance x. That is the distance from the plane to the airport. And then z is going to be the path of the plane. So we have to find z. And then ultimately we're actually trying to find dz dt because that is going to be the speed of the plane. So we know x is 10, dx dt is 240 miles per hour. dz dt we don't know, but I know 5 squared plus z squared is 10 squared, so z is 5 root 15 miles. So now I set up the equation 5 squared plus z squared equals x squared. Take the derivative of a constant is 0. So I get 2z dz dt equals 2x dx dt. The 2's go away. Z is 5 root 15, dz dt is what we're solving for. X is 10 and dx dt is 240. So now solve for dz dt and I get 480 over the square root of 15. When I rationalize, this becomes 32 root 15 miles per hour. So the speed of the plane is 32 root 15 miles per hour. Next, let A be the area of a circle of radius r that is changing with respect to time. If dr dt is constant, is dA dt constant? Explain. So pause the video, explain this, unpause when you're ready to check your work. Okay, so hopefully you said no. And we can see that, so if I set up the area equation, A equals pi r squared, and I take the derivative, I get dA dt is 2 pi r dr dt. So if dr dt is constant, that's fine, but dA dt is dependent on r and dr dt. So if r is increasing or decreasing, then dA dt is going to increase or decrease respectively also, just because dr dt is constant. So no, even if dr dt is constant, dA dt is still dependent on r. So if r changes, so will dA dt. So at a given instant of r, dA dt would be constant, but as soon as r changes, then dA dt is something different. Alright, number 3. A spherical snowball melts in such a way that the instant at which its radius is 20 centimeters, its radius is decreasing at 3 centimeters per minute. At what rate is the volume of the ball of snow changing? So here you need to use your volume equation for a sphere. So I want you to pause the video and try to find dV dt. Unpause when you're ready to check your work. Alright, so hopefully you got the volume of the snowball is decreasing at 4,800 pi centimeters cubed per minute. Make sure you put in decreasing. So when, let's back up at the top. So we know volume is 4/3 pi r cubed. If you didn't remember that, you could have looked it up. The radius at the instant we're looking for the rate of change is 20 centimeters. dr dt is 3 centimeters per minute, but it's decreasing at 3 centimeters per minute. So you could make this negative as well. I just chose to make it positive and recognize that in the end, when I'm carrying through the context of the problem, I want to emphasize that it's decreasing. So then I find dV dt, which is 4 pi r squared dr dt. Plug in r, plug in dr dt, and I get 4,800 pi centimeters cubed per minute. But again, it's important that in the context of the problem, I say that it's decreasing. Don't just say the volume of the snowball is changing, because we know how it's changing. So be specific with how it's changing. Number 4. A thin uniform rod of length y centimeters and a small particle lie on a line separated by a distance of x centimeters. If k is a positive constant, and F is measured in newtons, the gravitational force between them is below. So this is our function. If x is increasing at a rate 2 centimeters per minute when x is 15 and y is 5, how fast is F decreasing? So I want you to pause the video and try and find df dt. Your answer will be in terms of k, just so you know. So you will have k in your answer. Pause the video, unpause when you're ready to check your work. Alright, so here we should get F is decreasing at a rate of 7k over 9,000 newtons per minute. How do we come up with that? Okay, so we've got all of our information here. Now we know y is 5 centimeters, dy dt is 0 because we're going to assume that the rod is not changing in length. X is 15, dx dt is 2 centimeters per minute, dk dt is also 0 because that's a constant, and df dt is what we're trying to find. So first I rewrote f as k times the quantity x squared plus xy to the negative first. Now I go through the derivative using the chain rule and the product rule. So df dt is negative k times the quantity x squared plus xy to the negative second times the derivative of the inside, which is 2x dx dt, plus now I have to do the product rule, dx dt y plus x dy dt. Now I know this part's going to go away because I'm treating y as a constant in this case. So df dt is negative k times 2x dx dt plus dx dt plus x dy dt over the quantity x squared plus xy squared. Now I substitute in the values that I have, negative k times the quantity 2 times 15 times 2 plus 2 times 5 plus 15 times 0 over 15 squared plus 15 times 5 quantity squared. I get negative 70k over 90,000, which is negative 7k over 9,000. So now that's how I come up with F is decreasing at 7k over 9,000 newtons per minute. So the negative was telling me that it was decreasing because remember k was given as a positive constant. Last one. Train is traveling at 0.8 kilometers per minute along a straight track going east. A camera is 5 kilometers south of the track. Focused on the train, how fast is the distance from the camera to the train changing when the train is 1 kilometer from the camera? So pause the video, solve this, unpause when you're ready to check your work. I'll give you a hint, it is a triangle again, right triangle. Okay, so the distance between the camera and the train is increasing at 2 root 3 over 5 kilometers per minute. So how do we come up with that? Well, I drew my right triangle here. So this is the train. Here's the camera. Here, this distance y is 0.5 kilometers. Sorry, the 0.5, it's hard to read on my display here, but should be easier on your worksheet. X is the train, and z is the distance from the train to the camera. So I know dx dt is 0.8 kilometers per minute, y is 0.5 kilometers, dy dt is 0 because that's a constant. Z is 1 kilometer, dz dt is what I'm trying to find. I can use the Pythagorean theorem to find x at the instant when y is 0.5 and z is 1, and it's root 3 over 2, or I maybe recognize that this was a 30, 60, 90 triangle. So I could have gotten the root 3 over 2 that way as well. So now I set up my relationship between x and y and z. X squared plus y squared is z squared, so I take the derivative, 2x dx dt plus 2y dy dt plus equals 2z dt, dz dt. Substitute in, x is root 3 over 2, dx dt is 0.8, dy dt is 0, z is 1. So simplify, and I get 2 root 3 over 5 is dz dt. So make sure you're following the guidelines, take your time, do it right. There's a lot of room for error when we're doing related rates. The actual derivative part is nothing new from what we were doing, but coming up with the equation or equations to find the relationships between the variables is the challenge. Drawing the pictures in this case is usually not as big of a deal.